latency, or a video pass that allows 4K streaming, all processed in milliseconds at the edge of the network. Network slicing and network billing. Network slicing in 5G is a total game changer for rating engines. In the old days, a rating engine basically asked, how many bytes did they use, and what time is it? With network slicing, the engine has to ask, what kind of virtual network were they on, and did we actually meet the promised performance? One from volume-based to value-based rating. Traditionally, you paid for quantity, GBS. In a sliced network, the rating engine shifts to quality of service, QoS, parameters. Latency-based rating, a slice dedicated to remote surgery or autonomous vehicles requires ultra-reliable low-latency communication, URLC. The rating engine might charge a premium not for the data volume, which might be small, but for the guarantee of 5 milliseconds latency. Throughput guarantees, an 8K video streaming slice might have a floor price. Even if the user isn't actively downloading, the rating engine charges for the reservation of dedicated 100 Mbps bandwidth. Device density, for massive IoT, MIoT, slices, like smart city sensors, the engine might charge pennies per year for thousands of devices that only send a few bytes, focusing on connection density rather than data volume. 2. The dynamic SLA feedback loop. This is the most complex technical shift. In 5G, the CHF, charging function, and rating function are no longer blind to the network's performance. 1. SLA monitoring, the network continuously monitors if the slice is meeting its service level agreement, SLA. 2. Real-time penalties/discounts, if a gaming slice promised 20 milliseconds latency but the network becomes congested and latency spikes to 100 milliseconds, the rating engine can dynamically apply a discount or a refund in real time for that specific session. 3. Dynamic pricing, similar to surge pricing in ride-sharing, the rating engine can increase the cost of a high-speed slice during peak hours to manage network load. 3. Impact on rating engine architecture. To handle these complexities, the rating function has undergone a massive technical upgrade, multi-dimensional lookups. Instead of a simple table, user plus data equals cost, the engine now performs high-speed lookups across multiple dimensions, slice_ID plus latency _tier plus reliability _score plus location plus time. Edge integration, to keep things real-time, rating logic is moving toward the MEC, multi-access edge computing. If you wait for a signal to go from a cell tower to a central data center and back, the real-time aspect of 5G is ruined. Partner settlement, B2B2X slices are often sold to third parties, like an electric company. The rating engine must now handle complex revenue sharing where it calculates the cost for the end user, the slice provider, and the network operator simultaneously. 4. Summary of rating changes. Feature legacy rating, 4G, sliced rating, 5G, primary metric data volume, MB/GB, performance, latency, jitter, speed, pricing model static/tiered dynamic/SLA-based network visibility low, agnostic to pipe quality, high, aware of slice performance, target individual subscribers ecosystems, IoT, enterprises, partners. What's next? The next logical step in this evolution is AI-driven predictive rating, where the system predicts network congestion and offers users a cheaper slice before the network gets slow. Machine learning integration. In the complex world of 5G, a silent failure is a nightmare scenario for telecom operators. It occurs when the network successfully provides service to a user, but the charging function, CHF, fails to record or rate the event correctly. Because the user is happy and no alarm is triggered in the network, the failure remains invisible until a massive revenue leak is discovered weeks later. Integrating machine learning, ML, transforms the charging pipeline from a reactive rule-based system into a proactive, self-healing one. 1. The ML-driven detection architecture. To catch silent failures, ML models are typically deployed as a sidecar or an observation layer that monitors the stream of charging events without interfering with the real-time traffic. Data ingestion. The ML engine ingests data from multiple points, the SMF, session management, the CHF, charging, and the ABMF, account balance. The baseline, training. Using unsupervised learning, the model analyzes months of historical CDRs to build a normal behavior profile for every hour of the week, for every type of slice, example IoT versus mobile broadband, real-time inference. As live data flows, the model compares current patterns against the baseline. 2. Techniques for identifying silent anomalies. Standard rule-based systems check if a field is empty. ML looks for statistical deviations that rules would miss. A. Isolation forests. For outlier detection, isolation forests are highly effective at finding needles in the haystack. If a specific 5G cell tower suddenly reports 1,000 active data sessions but only 10 charging requests, the ML model isolates this cluster as an anomaly. A rule might miss this if the 10 requests it did receive look perfectly valid. B. Time series forecasting, RNN/LSTMs, the system uses recurrent neural networks to predict expected revenue volume. The scenario, if the model predicts $50,000 in revenue for a Tuesday at 2 p.m. based on past patterns, but the actual reported revenue is $35,000, it flags a revenue dip. The silent cause: this often points to a silent configuration error in a new 5G slice where data is flowing but the trigger is failing. See cross-domain correlation. One of the most powerful uses of ML is correlating network KPIs with billing records. The ML engine looks at the user plane function, UPF, traffic logs and the CHF records simultaneously. If it sees a massive spike in packet drops in the network that corresponds with a drop in charging events, it can pinpoint exactly which network element is causing the silent billing failure. 3. Root cause analysis, RCA, with explainable AI, XAI. When an anomaly is detected, it's not enough to say something is wrong. Modern 5G systems use explainable AI to tell engineers why the failure is happening. Example: AI output, anomaly detected in slice_ID_99. Correlation: 95% likelihood of a diameter to HTTP/2 translation error in the interworking function, IWF. Revenue impact, $1,200/hour. Capability legacy, manual audit, modern, ML integrated, detection time days or weeks, monthly reconciliation, minutes, real-time streaming, detection method thresholds, example alert if revenue $X, pattern recognition, statistical dips, scope known issues only unknown unknowns, silent failures. 4. Predictive self-healing. The ultimate goal of ML in 5G charging is predictive maintenance. By analyzing micro-anomalies, tiny patterns of failed requests that don't yet impact the total bill, the ML model can predict a total system crash or a major revenue leak before it happens, allowing the orchestrator to restart a failing microservice automatically. Storage of CDRs. In 2026, storing call detail records, CDRs, is no longer just about saving files. With the explosion of 5G and IoT, a single Tier 1 carrier can generate petabytes of data monthly. To manage this without breaking the bank or failing regulatory audits, the industry uses a tiered data architecture. Here is how modern telecom storage is structured. 1. The multi-tier storage strategy. Storage is categorized by how fast the data needs to be accessed. This is known as hot, warm, and cold tiering. +1 retention tier storage technology. Purpose period: hot 0 to 24 hours in memory, readies, aerospike, or NVMe. Real-time rating, instant fraud detection, and prepaid. Retention tier storage technology. Purpose period: SSDs. Balance checks, distributed SQL, cockroach DB, or all customer service lookups, bill disputes, and recent usage. Warm 1 to 6 months. Flash S3 analytics. Object storage, AWS S3 Glacier, Azure regulatory compliance, lawful interception, LI, and long cold 1 to 10 years. Archive, term ML training. 2. Modern storage architectures. Telecoms have moved away from monolithic mainframes toward decentralized, cloud-native solutions. Cloud data lake houses, solutions like Databricks, Delta Lake, or Snowflake are used to combine the scale of a data lake, cheap storage, with the performance of a data warehouse, fast queries. This allows a data scientist to run an SQL query against 5 years of CDRs to find churn patterns without moving the data. Software-defined storage, SDS. To avoid vendor lock-in, operators use SDS like Ceph or MinIO. This allows them to run high-performance storage on generic, low-cost hardware rather than expensive proprietary arrays. Compression and encoding, ASN.1/Avro/Parquet, raw CDRs are often stored in Apache Parquet format. This is a columnar format that is highly compressible, often 5x, 10x reduction, and allows for ultra-fast scanning of specific fields, example searching only for call duration without reading the whole record. 3. Compliance and security. The lockbox, CDR storage is heavily regulated by laws like GDPR, Europe, CCPA, USA, and local telecommunications acts. Immutability, WORM. For legal reasons, cold storage often uses write once read many, WORM, policies. Once a CDR is archived, it cannot be modified or deleted until its legal expiration date. Zero trust encryption. In 2026, encryption at rest is the baseline. Modern systems use identity-first access, where every single read of a CDR by a customer service rep is cryptographically logged and bound to their specific digital ID. +1 data sovereignty. Many countries now mandate that CDRs for their citizens must stay within physical national borders. This has led to sovereign cloud storage deployments where data is stored in localized, country-specific data centers. 4. The data gravity shift. A key trend in 2026 is bringing compute to the data. Instead of moving massive amounts of CDRs to an analytics server, the analytics agent runs directly on the storage node. This reduces egress fees, costs of moving data out of the cloud, and speeds up the time it takes to get insights from raw records.